As the speaker yesterday began talking about his PhD, I will start with this too. I obtained my PhD in Austria. And in Austria, we typically have a rule that when a talk starts, we need to determine a language. And the rule of thumb in Austria is, if there is a single person in the room who prefers English, the talk will be given in English, otherwise in German. I think there are maybe a bunch of people who might prefer English, so I will give this talk in English, following that Austrian rule, which one may discuss about, but that's another topic. So my talk will be about the golden ratio and the so-called Fibonacci sequence, and it should be a mathematical talk, but I will do my very best to address everybody here in the room. In particular, I will talk about linear algebra without using too much linear algebra, and the goal is to, at the end, to make everybody kind of happy. We'll start with these topics in two parts. Like, in the first part, I will talk about the golden ratio, and then about the Fibonacci sequence, and at the end, I will say something about the mathematical connections between them. So our first mission is to talk about the golden ratio. The golden ratio, that story begins in ancient Greece. So we talk about the ancient Greek world, and the people in ancient Greece, they wondered about the following question: whether numbers are commensurable. What does this mean? Well, think of a number in terms of a line which has a certain length. And so we imagine two numbers, one with a length A and another one with a length B. And by continuously subtracting the shorter one from the longer one, and then the newly become shorter one from the longer one, we wonder if there is a common measure, if there is a small unit that fits into the first length that we had and into the second length that we had. And the Pythagoreans, they had the idea that all the numbers, everything that we can construct with a ruler and a compass, must be commensurable. All the numbers that we can construct in a geometric world, they must have this property that they all share, that each two numbers share a common unit. And there was Hippasus of Metapont who made a construction that showed that there are numbers that are, or pairs of numbers that are not commensurable. And at the very beginning, I want to indicate the construction that Hippasus of Metapont made. So the first thing he did, he was constructing a regular pentagon, ein reguläres Fünfeck. And he could do so using only ruler and compass, Zirkel und Lineal. So let's do the following. We start with a single point. I hope you can see it. Then what we do is we take another point. And as we have 2 points, we can take our ruler and connect them by a line. That's all fine. So now we want to construct the point in the middle. That's something we can easily do. We take our compass and draw a line. And then, with the same length, we go to this point, draw another line, and these points will intersect precisely over the middle between these 2 points. So we connect them, and here we have found the middle of these 2 points. Well, very good. So with ruler and compass, we can construct the middle. Now, we repeat this construction and want to find the middle, the center, between these 2 points. So we take our compass, choose some specific length, we put it in here, draw this length, continue drawing until we have a point also down here. We go with our compass into that point and draw our circle. We connect these 2 points, and so we have found a point in the middle. So that's the basic construction that we need at the beginning. Now we go with our compass here into the center, and we draw a big circle. Because this point is in the very middle between these 2 points, we can draw a large circle. Very good. Now we extend this line up until it hits the circle. So we determine kind of the north pole, the upper point of the circle. Okay, and what we do now is we take our compass and take this point as a center and draw a circle that goes through this point. And at some point this circle will hit this point here, and it turns out that this length between this point and this point is precisely the edge length of a regular pentagon whose vertices sit on the circle. So all we need to do is we go with our compass into that point. This will be the center. We determine a circle that goes through this point and ask, where does this circle meet the boundary? And once we've done this, we keep our compass on precisely that length, go into this point, find another point. We go into this point, choose this point as a center, find another point down here, take this point as a center, find another intersection here, and if we do it another time, we end up here again. So connecting these 5 points gives us a regular pentagon. Let me remark, I did not prove anything. I claim that this is a regular pentagon and give you the construction. The gap that I leave is a proof that this construction does actually give a regular pentagon. So this circle closes up there, but this is kind of a gap that I generously keep. Okay, so what we have is a regular pentagon, and we kind of know that this construction can be made using ruler and compass only. So that's something we can construct. Okay, in particular, we can look at this pentagon and we can draw a diagonal, which means a line that connects 2 points on the pentagon that are not next to each other. So we can choose this point and draw a line. And now the claim that Hippasos of Metapont, that kind of shocked the Pythagorean world, the claim that he made is, well, look at these 2 lines. We have here the length of an edge, and here we have the length of a diagonal. We color this one red and this one green. So Hippasos of Metapont claimed these 2 lines are not commensurable. Since I explained commensurability at the very beginning, let me repeat. So the idea of commensurability, you can visualize it as follows. You take these 2 lines, the longer one and the shorter one, and you put them on the ground. Here's the longer one and the shorter one. And now, if you want to, think of the lines as fighting each other. And the fighting rule is the following. The green line and the red line, they fight each other. And always, as always, the smaller one wins. Winning means that the red one eats all the part of the green one that is up to its height, and the remainder of the green part falls down. And now we iterate this fighting procedure. Now we have a fight again. The green one is now the winner, eats up all the part of the red one that was on its height, and the remainder of the red one falls down. We repeat that fight, and so on and so forth. And the definition is these 2 lines, these 2 lengths are commensurable if this fight ends in a draw. If at some point the 2 lines have the same length. The Pythagoreans claimed that everything that we can construct with ruler and compass has this property, that when we put the lines next to each other, let them fight, after some point they reach a draw. And Hippasos of Metapont, he proved that for these 2 particular lines, we can go on. These lines get smaller and smaller and smaller, but we'll never have a draw. So his argument is surprisingly simple. And we'll look at it, and I will give this argument to you completely. So let's see what we have in our pentagon. What happened? Okay. So what we can do is we can draw all the other diagonals. And That's a very nice thing that we see here. It's a kind of a pentagram that you see in the center. And another thing that you see here in the middle is another regular pentagon, which is just the other way around, upside down. Okay, now we observe a few things. The first thing we can observe is that... Now I lost my... the first one that we see is here that the green line, the green diagonal, and the red line down here, they are obviously parallel. Both are horizontal. And the same thing happens when you look at this edge of the the pentagon and this diagonal of the pentagon. So also these lines are parallel. So what we have here, when we go this way, is a parallelogram. So a figure where the two opposite legs, the two opposite sides are parallel. So, and it's one property of the parallelogram that the length, say, of this red side and this side here are equal. So instead of looking at the red side at the bottom, we could say, oh, we look at this red side up here and forget about the fact that there was a red side down here. So now when we want the two sides to fight each other, let's see what happens. So in the first step we see the red one is shorter and it will eat up the respective part of the green one. Here we go. And the part of the remaining part of the green one, it falls down. Okay, what happens after a second step? Well, after a second step, we see now the green one is shorter. The shorter one wins, eats up all the part of the red one. And now we don't let the red one fall down, we just draw it this way. So after two fights, we know that the relationship is like we end up with these two lengths. And now we do a little more geometry. Look at the following. I already mentioned to you that there is a pentagon in the middle. And also this this pentagon in the middle, it also has diagonals. The same business as always. And now we change our focus. Namely, we look at this parallelogram. Let me see how I'm too close. We go up to here, we go there, we go up, and we go backwards. So it's kind of a little gray. I don't know if you can see that. Yeah. Wonderful. So this again is a parallelogram because we know that when we have a regular pentagon, that one edge is parallel to the diagonal on the opposite side. So we know that these two lines must be parallel. And of course we know that this edge is parallel to this guy. So we know that these two lines are parallel. So in the end we have a parallelogram, and we know that this green edge is not just here in its length, it's also down there. Which is lovely, because now we say, well, after a couple of fights, the previously red edge down here and the green edge down here have converted into some new edges, a red edge of a pentagon here and a green diagonal of a pentagon there. So we can now go in and continue with this game. We can look at this pentagon, and in the middle we see again another pentagon. So after some more fights between red and green, we see, well, will be this red edge and this green edge fighting against each other. So we have another pentagon. But nested within this pentagon is yet another pentagon down here. So we could continue with this game, and we'll see that the lengths of the red and the green edge that we have after always a couple of fights will always be an edge and a diagonal of smaller and smaller pentagons nested within each other. Therefore, our fight can never end up in a draw, because after a couple of fights we'll always have an edge which is shorter and a diagonal which is longer. So after fighting and fighting and fighting, no matter how long we fight, at some point we'll or at every point, we'll always have a shorter and a longer one. So this fight cannot end up in a draw, which means these lines are not commensurable. So this was the proof of Hippasus of Metapont. The Pythagoreans kind of were in deep dispute, and then a little later, Hippasus of Metapont, he drowned in the sea. Like he died on the sea, and there's kind of, Laura probably knows better. There's rumor whether it was the gods that drowned him, the Pythagoreans, or just an accident. We don't know. However, this was the story of Hippasus of Metapont, and that's his proof that there are lengths that are not measurable in terms of, or not commensurable. Okay, I want to show you another thing about the Pentagon. Let's call this edge length A, whatever it is. Think of A equals 1 or whatever number you like. And the length of the diagonal should be called x. And we wonder what can be said about the ratio between x and A. Or in other terms, if we choose A equal to 1, what could be said about the length of x? Oh, that's some question. And we can also solve it easily. Now the same color means we have two parallel lines. So same color does not mean same length, but here it's just parallel. So we have the red edges. Now we can draw this diagonal here. And we already know this diagonal is parallel to this edge, which is good. We can draw yet another diagonal, this one here, and we know that this diagonal is parallel to this guy. So if we look at what we have, is we see two, how do you say in English? Similar triangles. Similar triangles. We see a triangle down here, and we see a triangle up there. So we know something about the ratios. Let's first determine the lengths of the edges that we have. So up there you see a green edge, which has obviously the same length as down here, the red one, because we drew a regular pentagon. Okay, then we know something about that diagonal. The diagonal has a total length of x. And I also marked it for you, I guess. No, I didn't mark it for you. Here we see a parallelogram. We have two blue sides and two green sides. So, well, not necessarily a parallelogram. Oh, yes. Yes. Yes, we have one. So this is also A. Yeah. Since we know the total length of the diagonal is x, we know that the remaining piece is x minus A. So, and now it's just a matter of computation. We need more space. So we say that A divided by x is the same as x minus A divided by A. And that's something we could try to solve. We multiply each side by A, and we multiply each side by x. Since A and x are both larger than 0, there is no information lost, so we have an equivalence. Then we get everything to one side, and then we apply whatever you like, the PQ formula or the ABC midnight formula. The latter one is something I always forget. I always tell my students, like, oh, now we should solve these things, and then I'm lost because I forgot this formula, and typically students are enthused about that. Oh, well, this guy always forgets this formula, and well, then we need to recall what's there. Fortunately, here I made it on slides so I could prepare, and I found the solution for you. So the solution is this one. So it says that x is nothing but A times this number. So there are two solutions because we have a quadratic equation. It's 1 plus the square root of 5 minus 2 divided by 2, or it's 1 minus square root of 5 divided by 2. Here in our case we could observe, well, if we take a plus, this number is around 1.6, and if we take a minus, this number is around negative 0.6. In our case, x is obviously larger than A, so we would choose the positive solution. So we know that the ratio between x and A is 1 plus square root of 5 divided by 2, which is the so-called golden ratio. So we see if we have, say, a regular pentagon whose edge length is 1, then we know the length of the diagonal is just the golden ratio. So that's one very cool thing. I wanted to add something else. And what I've written there is pure rubbish. Like, at least for mathematicians. Mathematicians would say this. No way. Maybe for computer scientists, this would be sufficient. I don't know. So, to be honest, we should say, well, if you use your calculator, we could ask what's pi, and then we get what you expect. So, to be honest, we should say that's 3 plus a bit. Okay. Now I want to do the following with you. I want to quantify that bit. So I go to my calculator and say, well, take this number and subtract 3. So we get 0.14 and so on. So this is what we have as a bit. Okay, this bit is smaller than 1. And I want to express it in the following way. Since it's smaller than 1, I want to express it as a fraction. And I want to write a 1 in the numerator. And I wonder what's in the denominator. So in order to find out what's in the denominator, my calculator fortunately has a button which tells me take x inverse. So I press that button, and what comes out is this number. So yes, that's what I would have to write into the denominator. And as you know me, in the meantime I'm lazy, so I write 7 plus a bit. Okay, 7 plus a bit. Let us quantify that bit. We take what we have here, we subtract the 7, so we have here the value of a bit. Okay, we want to go on with this procedure. So instead of a bit, we want to write 1 over something. Okay, so in order to see what we need to write down here, we take the value that we have, we invert it, and what comes out is this. Oh, that's nice. That's 15 plus a bit. So in the meantime, you know how the story goes on. I subtract 15. I want to express that bit as 1 over something. So I invert the remaining bit that I have. And that's now really 1 plus a tiny little bit. So I want to go on, want to quantify that bit. I subtract 1. I invert the value that I have in order to write it as 1 over something. And when I invert it, holy shit, I get 292 plus a bit. And at this point I stop. I've seen how the whole thing works. And I can make a nice observation. This here is really a tiny little bit. 1 over 292, let's forget about it. So we take, say, that's approximately, and instead of 1 divided by 292 plus a bit, I say let's think it's 0. So, and now we can go backwards. We can say, well, 15 plus 1, that's 16. 7 plus 1 divided by 16, that's 113. Oh, sorry. That's 113 divided by 16. And now I have 1 divided by this, so that's a double fraction. And I add 3 to this, and what comes out is 355 over 130. And that's a surprisingly good approximation of pi. So if you put this into your calculator, you see pi is something like this. And what you have on the right side is something like this. So the first difference that you actually have is 1, 2, 3, 4, 5, 6, 7 on the 7th decimal place. And you wouldn't expect that, because here in the denominator you have just something about around 100, and having a difference only at the 7th decimal place, that's kind of a surprisingly good approximation. Okay, now, why did I tell you that? Recall what we did in our computation. We wrote pi in this way as a so-called continued fraction. And I said we go on, we have a 3, we have a 7, we have a 15, we have a 1, we have a 292. And at that point I said, well, this is more or less 0, because this number is so incredibly large. And then I went backwards and obtained this good computation. Now let's be mathematicians. Mathematicians need to be creative. Mathematicians need to play around with things. And let's wonder what would be the number which has the worst approximation. Like here, our approximation became eventually good because we got a large number here. I could wonder what is the worst possible way that I could construct a number where this trick does not work. And the answer is, well, I could start with such a continued fraction and take always ones. So I keep the numbers in the denominator really small. 1, 1, 1. And so on. So this number would be, in some sense, the worst number to approximate with rational numbers. So what's that number? And the cool thing is we can easily compute it. Observe the following. We call that number x. What we can do with this x is look at the lower part down here. If you look at this lower part, you will see this lower part is precisely the same x as the total part. So when I look at the total part, this thing continues ad infinitum, is always continuing. And if I take only that lower part, I see precisely the same picture as the full continued fraction. So we know that this x must be the same as 1 plus 1 divided by the same x again. Well, that's cool. That's an equation. That's an equation. It has only one x. We can run algebra on it. Let's try to solve it. What we do on both sides, we multiply by x. So we have x squared is equal to x plus 1. We bring the x and the 1 to the other side. So we have x squared minus x minus 1 is equal to 0. And that's something we can do with our PQ or ABC or midnight formula as you like. And I did that for you. What comes out as a solution? The golden ratio. So in our case, we have our x determined as 1 plus a bit. So we should take the positive solution. So we see, well, we obtain the golden ratio in some sense as the worst number to approximate by rational numbers. Okay, now I spoke really long about the first chapter. And I want to tell you now a little bit about the Fibonacci sequence before eventually coming to merging these two. So about the Fibonacci sequence, well, here's the picture of Fibonacci. Actually, the Fibonacci sequence was known before. Like in ancient India, they are wondering about Sanskrit grammar, and Sanskrit poetry consisted of long syllables and short syllables, and they wondered how we can arrange them. And already a few hundred years before Christ, there was Panini, who was a Sanskrit, well, he wrote big essay or big Sanskrit grammar, but also wondered about arrangements of syllables. And many years later, many centuries later, but still a little bit before Fibonacci, there were other Indian people, like Hemachandra, who will be projected here, who kind of did this in a more systematic way. And I want to show you what questions they were interested in. So the basic idea is, we saw that definition also yesterday. The first Fibonacci is 1, the second Fibonacci number is also 1, and for all later ones we define the nth Fibonacci number as the sum of its two predecessors. Okay, so the Indians had this looked at this series as well, and what they were interested in was poetry. Since my Sanskrit is not very good, and my Latin is a tiny little bit better, I thought we should use this occasion to have something in Latin. So I selected 3 lines from a Latin poem, and this poem is about Icarus and Daedalus, who were captured on an island, and they were captured by King Minos, and they couldn't flee because, well, it was an island, and then they decided, well, we should flee through the air and construct wings, and you know how the story continues. So in Ovid, he kind of wrote a poem on that. And so I read it 2 times to you, the first time now. Omnia possideat, non possidet aera minus, dixit et ignotas, animum dimittit in artes naturam conovat, naponit in ordine pennas. So the idea is, there's no rhyming at the end. If you look at the end, there's absolutely no rhyming. The important point in Latin and also in Sanskrit poetry is that we have an arrangement of long and short syllables. So there are rules when a syllable is long and when short. In our case, for a long syllable, I draw such a line. So this word is called omnia. So om is long, and nia, these are 2 short ones. So this is a 3-syllable word, counting 1 long syllable, 2 short ones. Omnia pos. When there are two consonants coming, we say, well, this syllable ends on a consonant, so it must be long. So there are certain rules. Omnia possideat. Non possidet aera minus. Something like this. And you can continue with this analysis throughout the lines, and you see that there are essentially 2 parts, two forms of construction. Either you have such a block of a long syllable and 2 short ones, which comes there again, or you have a long syllable followed by another long syllable. And that's essentially everything that can happen, more or less. So we have either long, short, short, or long, long. And there are 6 blocks of these guys, so the meter is called the 6th measure, the hexametron. Okay. Now, we use either this or this. And the rule of thumb is that a long syllable needs twice as much time as a short syllable. So, long syllable, short syllable could be written like this. We have 1 block of a long syllable and then 2 blocks, each filled with a short syllable. And this one is filled like this. So, now mathematics comes into play. We could wonder, what is it like, on how many ways could we fill 4 units of time? And well, we could either fill it in the most boring way by filling 4 short syllables. We could also say, well, we want to use 1 long syllable. So this long syllable could be at position number 1, and then we have followed by 2 short ones. Or we could say the long syllable is in the middle. Or we could say the long syllable is at the end. Or we could use 4 long syllables. Like, from a poetic point of view, this doesn't make any sense. Like, as you see, in our poem, the magic of the poem is that only these 2 kinds are used. But now we come as mathematicians and ask, well, in theory, how many ones could we build using these 2, the long and the short one, that fill up 4 units of time? And we see, when we count them, these are 5. 5 is among the list of Fibonacci numbers. 1, 1, 2, 3, 5, 8, 13, and so on. There's a 5 in there. So now let's repeat that question, ask, well, if we didn't have 4 units of time, but we have a 5th unit of time, how many possibilities were there? We can count them. I listed all of them for you. And when we count them, we see these are 8. Well, that's good. We're still on line with Fibonacci. Recall it, it's 1, 1, 2, 3, 5, 8, 13, and so on. So let's try with n equals 6. What do you expect? Well, it should be 13 possibilities. I wrote them down all for you, and you can count them. It will be 13. So, magic. Let's try to prove that. Let's try to formulate a theorem. Our theorem looks as follows. The number of different feet, so feet is such a block consisting of certain units of time, and the number of feet with n units of time is the n plus 1st Fibonacci number. Okay. We do this by induction, and the concept of induction, I think almost everyone in the room knows it. The basic idea is we show that this is true for n equals 1. We think of a domino piece for that, And then instead of showing it separately for n equals 1, n equals 2, n equals 3, n equals 4, which would never give us the complete solution, what we do is we show it for n equals 1, and then we show when it holds for n equals 1, it must hold for the next value as well. So it must hold for the next value as well. And by this we can kind of get the complete result. And that's what we do. Let's start with the first two ones. So n equals 1. If we have just a single unit of time, there is precisely one way to fill it, namely using a short syllable. That's good. That's the second Fibonacci number. So if we had 2 units of time, there are essentially 2 ways to fill it. Either with a short and a short syllable, or with a long syllable. And that's the third Fibonacci number. Recall, first Fibonacci number 1, 1, 2, 3, 5, 8, and so on. Okay, so we know the beginning is clear. We know for small values of n we're done. So now let's think of such a long foot consisting of n units of time. And the idea is, well, we look at the end. At the end, we have 2 possibilities. Either the last syllable is a short one. Then we have to fill the remaining n minus 1 syllables with long and short ones. Or the last syllable is a long one. Then we have to fill the last n minus 2 syllables with long and short. The remaining n minus 2 units with long and short syllables. So for the first one, we have, by the induction hypothesis, Fibonacci number of n many possibilities, and here we have the Fibonacci number of n minus 2 many possibilities. And if we add those two, we use the construction rule for Fibonacci numbers and obtain that the total number of possibilities is just the sum of Fibonacci number of n, Fibonacci number n minus 1, and that's the Fibonacci number of n plus 1. So this was kind of the background where the Fibonacci numbers occurred in ancient India. And if you get bored at this point, you could wonder, well, how many possibilities were there if I had short syllables and the long syllables didn't last twice as long, but 3 times as long as a short syllable. So now you could wonder what kind of alternative to Fibonacci numbers you would get. And this is a fun thing to play, but I don't want to go into detail here. That's just an exercise if you want to solve that. Connections. So I told you about the golden ratio, about the Fibonacci sequence, and now I should say a few words about connections, and this is where linear algebra comes into play. So for those who haven't had the wonderful opportunity to do some linear algebra here, take it as a motivation. This is really a meaningful lecture. So let's write down the Fibonacci numbers. 1, 1, 2, 3, 5, 8. And if you watch the video by Arthur Benjamin, he has that nice saying. He says 1, 1, 2, 3, 5, 8. Who do we appreciate? And then Fibonacci. So we continue. 13, 21, blah, 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 blah. I write them down up to 1,000. So, and now we do something magical. We don't take the sequence as it is, but we look at this sequence from a more general, from a higher point of view. We take this sequence and look at it in the plane, in 2 dimensions. And from this, looking onto that sequence in 2 dimensions, we see the true beauty, I claim, the true beauty of this sequence. So, what do I mean? Take a coordinate system. And now we take that sequence on the right, and we start by the least 2 points, and by the least 2 numbers, and we take them as a point in the plane. So that's 1, 1. Okay, here we are. Then I move up my brackets. I get 2, 1. That's another point in the plane. Here we are. I connect these 2 points, but the connection doesn't matter. Okay, the story goes on. I move my brackets upwards. I get another point in the plane. This is 3, 2. I move my brackets upwards. I get 5, 3. I move my brackets upwards, I get 8, 5. I move my bracket upwards, I get 13, 8, and now there's no more space. Here's something mysterious going on. These things seem to become very linear. And we'll discuss this in a second. Before we discuss this, I want to make another observation that will be essential at the end of the talk. So when I have one such point, say this one, 3 and 2, and I want to go to the next point, I apply some transformation. And the transformation looks like this. I have a point, say 3, 2, and then the next point consists of the following. What had been the upper coordinate becomes the lower coordinate. This corresponds to moving the brackets upwards. And instead of that y, which gets lost, the new point will be x plus y. So this will be our transformation that leads us from one point to the next one. And this transformation is a particularly nice one. If you have attended your class in linear algebra, you will know this notion. It's a linear transformation. In German, eine lineare Abbildung. Linear transformation means that we can do nice things with this, and I just mentioned it. I will explain in the example why this is useful. So with linear transformations, you can do the following. If you apply them to some vector, but not really to the vector, but like a stretched version of the vector, you could instead apply it to the vector and stretch afterwards. So you can take out scalars. Okay, that's one nice thing you can do. And another nice thing you can do is you can split it over sums. So if you want to know what comes out when I take my f and apply it to v plus w, you could first apply it to v and then apply it to w and then add the two vectors. So these are two properties that our map has that you can easily check using pen and paper, but I don't want to bore you with this. Let's just keep it in mind. At the end, this will be extremely helpful. Okay, so I claimed this looks very linear. And I wanted to convince myself that this is really linear, but unfortunately my numbers turn large very quickly. And in order to see large numbers, what you could do is you move to a logarithmic scale. So now we take a coordinate system, and instead we take a logarithmic coordinate system. So we don't have 1, 2, 3, we have 10, 100, 1000, and we do this on both axes. If you haven't seen that before, fall asleep for 2 minutes. So we could start with our Fibonacci sequence and just write it there and see what's happened, whether it's actually a line. So here's 1, 1, and we enter our numbers. This looks lovely. This looks really, really like being a line. Okay, now let's have some fun. I take another sequence, and I define my other sequence as follows. I take two other starting values, like here, 9 and 33. And then what I do is I apply precisely the same transformation. So the next number in this sequence would be 33 plus 9, that's 42. The next number in the sequence would be 42 plus 33, that's 75, and so on. So I take this number. It's just the same transformation, but starting at a different point. So let's draw these points and see what happens. Here is my 33, 9, and we draw. And it goes into the same kind of thing. It's like it's going up and down a bit, but in the end it's going the same way. Okay, let's play a little more. Take a point which is really far off. I took a third sequence. It's starting with 110. So here are the numbers that we get, and the first point has as first coordinate 10 and as second coordinate 100. So it's somewhere up here. I drew it for you. And let's play the same game. Let's see what comes out when we apply our drawing of a point. It goes really far down. It goes up, down, up, down, down. Goes into the same direction. This line here seems to be very attractive. And we have some bouncing behavior, but in the long run, everything is kind of pulled towards that direction. So, in the end of the talk, I want to discuss with you what it means to pull into a direction. Do you know at which time I started? I don't want to...
You started at 10:20?
Holy shit! Okay. So, we wish we had such a line. And we don't know whether this attracting line exists. But it seems when we have our curve, our Fibonacci numbers, that we have some bouncing behavior and then it's torn into that direction. So if we had this line, our dream is, so I don't claim we have this line, but if we had it, our dream would be the following. Let's look at this at another scale, that when we have a point that's on that line, there would be no bouncing upwards and downwards, and vertices would just be pulled into that direction. So now we play the game the other way around. We say, well, can we find a point that has the property that by our transformation, this point is just sent to a multiple of itself? So that's the idea. We want to find a point on that line, say, whose first coordinate is some x that we don't know, and the second coordinate is 1. And we ask, well, our point should have the property that it's sent to a multiple of itself. So the point that we obtain when we apply our transformation to x1, well, that's easy, we know that. The second coordinate is x, and the first coordinate is the sum of the two. So we want to have a vector with the following property, that the new point that we obtain is simply a multiple of the point that we started with. So that's again the idea. We would like to find a point on that line. We have no idea about this line, but now we're looking instead at a point, and if it was on the line, and the line was as magical as we dream it, then this point would have to be sent to a multiple of itself without any bouncing. Okay, so that's something we could solve. That's a linear system. We have two unknowns. We have the x and the lambda. So we can solve it, and I leave out the details because they are boring. There's no much math behind. But what you see is that this value x is the golden ratio. And the value lambda, the scaling factor, is again the golden ratio. Isn't that beautiful? So we want to apply this. So when we have a point which is on that line, and like that's the point we constructed, and we apply our transformation to it, it is scaled by the golden ratio, 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 no bouncing at all. So we see in some way, points on this line are scaled by the golden ratio. If we look at our computation, that I was really going quickly through it, we see that our computation has not just one solution, which was the golden ratio, but also another one. There is one more vector that is sent to a multiple of itself, namely this vector here. And we could see what happens with this vector. This vector is sent to a point down here. And if we iterate the procedure, it's sent to a point here, it's sent to a point here, and so on. So there are two kinds of points. The first one is on our magical line. It's sent off to infinity without bouncing. And this line has kind of an attractive behavior. If we start here, we get a bouncing towards this direction. But if we start on this line, we have no drawing into this direction. We have just a bouncing upwards and downwards, and the amplitude of the bouncing gets smaller and smaller. In other words, which I skipped for time reasons, here we have a scaling factor of negative 0.618. Great. How can we use that? And that's really close to my conclusion. Imagine we have a point, and we want to compute what's going on in the long run with this point. Well, then we could say, we can decompose this point as one point, which is on this line, plus one point, which is on this line. And now remember what I told you about the linear transformation. When we have scalars, we can draw them out. When we have sums, we can tear them apart. Which means if we want to compute what's going on with this point when we apply our transformation, we could apply it separately to this point and to this point and see what comes out. So this point here, it's stretched by a factor of 1.6. So it moves somewhere up there. And this one is multiplied by a factor of negative 1/2. So it goes down there. So we know the next point will be there. Namely the combination of this point, or the sum of this point and this point. Again, if we want to compute the next point, well, this point here is scaled by 1.6. This one here, the other one, is scaled by negative 1/2. So we get up there, and here's our third point. So by this point of view, with these two lines, they are called Eigen Spaces, and these will be the eigenvalues. We have an explanation for that bouncing behavior. Into one direction, we are torn away, or we are pushed away by this with this speed. And the other direction, it scales up and down, but because this number has an absolute value which is below 1, that scaling gets smaller and smaller and smaller. And this explains why the whole story taken together is going towards this direction, and the amplitude as we go out is smaller and smaller. This can be used for two things. First observation. Recall that this line here is a line that has a constant slope, and the slope has the property that when we divide every x by y, it's just the golden ratio. This is just our construction. When we take the Fibonacci sequence, we see that our points converge to points of that line because they are pulled into that direction, and the amplitude of the waves gets smaller and smaller, which means our points converge to points on that line. So when we take a point which is far away, this point has as coordinates two Fibonacci numbers, and as this point is really, really close to our magic line, we know that the ratio of the fn plus 1 and the fn is really, really close to the golden ratio. So that's a proof for the fact that you see in the Arthur Benjamin video on our side. The last slide. Almost last slide. Last slide. I promise last slide.
You don't
No, I'm in a rush. I want to don't overdo it, and I'm already over time. So this is what we had. And I want to give you just an idea about that formula that we saw yesterday that explains the computation of Fibonacci numbers. So if we want to know, like, what is the nth Fibonacci number, we can use the technique that we saw. So let us focus on this small part. Here it is. And here is our first pair, our first point. And now we could say the following. Well, couldn't we just decompose this point as a sum of 2 points that are on the first and on the second coordinate, on the first and second line? And then we know, well, if we apply our transformation a couple of times, this point gets sent at a speed that we know precisely. It gets always factored or multiplied by the golden ratio towards this direction. And this point will have a bouncing behavior, which we also know very precisely. So we could use this information to compute the coordinates of all further points. And that's precisely what we can do. So, so that's something that I won't go too far into detail. We know these points, or we know these vectors on the lines precisely. First coordinate, or the y coordinate is 1, and the x coordinate was the golden ratio. And also these lines we know precisely, like these are certain numbers that we know. And now the cool thing is we can determine how often we need this vector in order to get a point which gives precisely the part of this point projected onto this axis. And we can compute how far we have to go in this direction to get a point that is directly under this point. So we can compute alpha and beta, and alpha and beta look like this. Really, don't worry about the details. You can do it as an exercise. This is just a bit pen and paper work. And the cool thing is, now we know, so to say, the coordinates alpha and beta. We know how far we have to go in this direction and in this direction to address this point. And now when we iterate our procedure, we just have to say, well, if we iterate it one step, then we'll have the second Fibonacci number down here. If we iterate it again, then we have the third Fibonacci, the fourth Fibonacci, the fifth Fibonacci number down here. So we just iterate our procedure and look at what's in the lower coordinate. So, and if I do this, well, that first coordinate gets scaled by phi, and that second coordinate gets scaled by negative 6.1. So we can compute what's the second coordinate of the nth of the vector obtained after the nth application of our transformation. And if we add this up, we get precisely the formula that we had yesterday, written a little differently because I was hiding the less beautiful part in these two symbols. So this is a formula which we can use to explicitly compute Fibonacci numbers. And even though I didn't explain you all the details, the idea is just a decomposition into a suitable basis. And then you see what's going on, because one basis vector stretches out and the other basis vector just gives some waves that get smaller and smaller, and in the end do not contribute much. And this is just this small part. So that was everything. I plan to say a few more words about how you can use this technique to measure books or the quality or importance of websites, but I'll skip that and instead thank you very much for your kind attention.
So that you can tell us about how can you do that on the website. You know, the last part. We are so sad that you're not telling the last part.
Yes, but as you see, this is my very last slide. So telling the last part would just be taking a few more minutes, and this was just a joker topic, and essentially the idea is really the same, and Joachim would be really helpful because would be really happy because this now goes into questions of Markov chains, and so then the basic idea is, if you want to measure how important journals are, scientific journals, the model is we go into a library, choose randomly a book, read it, choose randomly a reference in that book, go to that reference, choose randomly another reference, go to that reference, and so we have a random walk through the books in our library. And then we can compute the average time that we spend, or the likelihood that after a year of running through the library we are at a certain book. And this is often taken as a measure for the importance of books or journals. And the idea behind that is you also have such a space, and one eigenvalue is is 1, and the other eigenvalue is below 1. And it shows
That's
you
positive.
how... Yes. It shows you how quickly these things reduce, and so that's Perron-Frobenius business. And it tells you essentially after, you don't have to wait for years, you can wait a tiny little bit and then you see the importance. And that's what they do in practice. Like when Google wants to determine how important websites are, they don't compute these eigenvalues. What they do is they run this matrix a couple of times, and at some point they see there is no much fluctuation, and if there's not much fluctuation, they are happy. So that's a quick way to compute things. As we saw here, the Fibonacci numbers, after only a tiny little bit, they were so close to that line. And if you're working in practice, you don't worry about so close is the same as equal.
Thank you very much. This motivates the course on positive matrices. We're planning linear algebra for next term and adding stuff around Frobenius as well. So thank you. This was a fantastic talk. And do you have questions? Okay, so I have a question. Could you, I know that you went very quickly, but you know, the behavior, you see with the help, there. That basis is orthogonal, everything is fine. And the fluctuation, does it converge? I mean, in this one here, you fluctuate?
Yeah, absolutely. You have a scaling factor whose absolute value is below 1, so these things get smaller and smaller and smaller and shrink together after a few steps.
Yeah.
Because we are so lucky that this value is smaller than 1. If it was larger than 1, then the whole thing would blow up into something. So here the cool thing is, once scaling factor is large, it pulls everything out at exponential speed. That's why we saw on the logarithmic scale like constant points. And this guy is below 1, so after the steps out, this amplitude, that shrinks, that goes smaller and smaller and smaller and smaller. And so after a few steps, we're almost there. And that's also what Art Benjamin kind of... Where's his slide? I don't have his slide anymore. It's gone.
Okay.
Whatever, yeah.
Do you have more questions? I have...
I'm trying to bring this in connection with the equilibrium ideas when we calculate general equilibrium conditions. And it's nice to think about a plane, but how do I know when I first come across a problem how many dimensions I actually need in order to specify whether I will end up with divergence or convergence?
If you take that problem that we had with the syllables, I said, well, we have the long syllable, which lasts twice as long as the short one. If I had said that we have a syllable which lasts 3 times as long as a short one, then we had to involve a recurrence relation that involves not just the 2 last, but the 3 last syllables.
And so a dimension is the same.
So I need a third dimension, because my recurrence property now involves 3 components, like the newest one. In order to construct it, I don't need only the 2 predecessors, but the 3 ones. So I need 3 predecessors to determine the next one. So we have a 3-dimensional picture. I don't know if this is a good and complete answer, but this
is
pops
a good
up.
answer. But if I think along these lines and keep going, then it seems to me that by adding dimensions, I would always get some sort of commensurability. Whereas, and catch me where I'm missing something. And then if I go to the concepts in theory of mind, where our essential quantification and operationalization of observed behavior always hits the burden of incommensurability, then if there is a mathematical proof that by adding dimensions I can turn everything to commensurable, that problem is essentially solved.
Probably spontaneously cannot contribute.
But we can think of it.
Yes, so we should discuss.
Yes, please.
You should explain to me a little more detail.
Yes, so it's very nice to connect theory of mind.
Yes, we have points to discuss.
Yes. So if there are no more questions, I